And it's my great pleasure to present our today's speaker, Professor Milos Arsenovic from Belgrade. And the title of his presentation is Gradient Estimates for Harmonic and Generalized Harmonic Functions. And thank you very much for agreeing and deliver a talk at our seminar, Professor Milos Arsenovic. And please go ahead.
Thank you, Alexey. And first of all, it's a real pleasure again to see at least online people that I know, and to also to have listeners which I haven't met before, but I do hope to meet them. And this is the talk about basically classical topic of gradient estimates for certain classes of functions, and you can imagine all kinds of classes of functions, analytic, for example, and so on. And it's a huge area, and there will be talk on two rather special topics. And as you see, the title is for harmonic and generalized harmonic functions, but I'm going to talk at first about generalized harmonic functions, and then in the last part of the presentation, I will talk about the harmonic case. And this topic of generalized harmonic functions, this is joint work with Jelena Gajic, and the second part regarding harmonic functions is a joint work with Professor Mateljevic. And now let's start with these generalized harmonic functions. You can generalize them in many different ways, and one way is to replace the ordinary Laplace operator by this operator, which involves two complex parameters, alpha and beta, and this is the formula, basically. Someone might wonder, why do we have this factor 1 minus modulus of z squared in front of the operator? But that comes from geometric considerations. In some cases, it can be interpreted as a Laplace-Beltrami operator in some cases. And so this is the operator. It's going to act on functions which are defined in the unit disk, right? And the principal term is this one, which is essentially the Laplace operator with a constant 1/4 in front, right? And it has this factor 1 minus modulus of z squared in front of it, which tends to 0 as you approach the boundary of the disk. Then you have this first order parts, dz and dz bar, with some factors in front of them, and minus alpha beta. So the first thing that you notice is that this is clearly elliptic operator, even uniformly elliptic second order operator in the unit disk, but it degenerates near the boundary, because the principal part, this factor 1 minus modulus z squared, does not dominate alpha z and beta z bar as you approach as you go to the boundary, except, of course, in the very special case when both parameters are equal to 0. So now let's take a look. If you take that alpha and beta both are equal to 0, then it's something, a function of z times the ordinary Laplace operator, right? And now we are going to investigate the properties of functions u, which satisfy the equation L alpha beta u equals to 0. These are called alpha beta harmonic. And of course, they form a vector space, and it's denoted by H alpha beta on the disk. Now, special cases appeared in the literature in addition to investigations which were focused on the general case for any alpha and beta, general complex values of the parameters. So these last two points, point 4 and point 5, they deal with one parameter cases, and when one parameter is a real number. So 0 alpha harmonic functions are simply called alpha harmonic, alpha real greater than -1. And again, if the parameters are equal and usually denoted then by alpha over half and real, then these are T alpha harmonic functions. So we'll come to these special cases later on. Now, what were the origins of all of this? I mean, they appeared in almost half a century ago in studies which are related to HP theory for the Heisenberg group, right? And upper I mean, Siegel space. And then this is then that happens in several complex variables, and Z times partial derivative with respect to Z and Z bar partial derivative with respect to Z bar. These are replaced by these operators, which are standard in the theory of functions on the unit ball in CN. This is this paper by Geller, 1980. And then later on, see, in 1996 appeared a very important paper by Acher and Bruna Cascante, which we here in Belgrade like to call ABC paper, with many results regarding generalized M-harmonic functions. So we are looking at a special case in the unit disk, and it's worth mentioning yet another paper which deals with the case of the unit disk as we do. This is this paper by Klindborg and Olofsson. Olofsson had many papers written on topics like this one. So that's relatively recent paper, 2021. Now, to get this theory started, we need to have at least some examples of alpha beta harmonic functions, and this is the one you see on the screen. U alpha beta of Z is given by this formula, and if you think for a moment, if you take that both parameters are equal to 0, you will see that you basically get the Poisson kernel for the unit disk, and this generalization will play the same role in the theory. It will be used to construct this kind of Poisson kernel for the alpha beta harmonic functions. Now you see, this is the function U alpha beta. We're going to talk about pointwise and L1 estimate, and this is a theorem by this paper by Klindborg and Olofsson. It first says that this is alpha beta harmonic. That's done by simple calculation. Then you have pointwise estimate, this one, which is kind of trivial, just calculate. But it's important to notice that the estimates very often involve the real parts of these complex parameters, alpha and beta, as you see here. And then finally, and very important, the last one is perhaps the most important, this is the L1 estimate. You see, you estimate the L1 norm of this function U alpha beta on the concentric circles of radius R. And this is the uniform estimate, right? The right-hand side is independent of R. So you're going to get something like these approximations of identity, mollifiers, whatever you call them. And now, since the topic is the estimates of the derivatives, clearly we need the derivatives of this U alpha beta functions, and you get them here. That's Klindborg and Olofsson. It's very well written paper, which simply gives you lots of formulas which any researcher can use. So these are derivatives. And now we have higher order derivatives also present in that paper. Derivatives of order k. These are the derivatives with respect to z, not with respect to z bar, but there are analogous formulas for the derivatives with respect to z bar. And later we will generalize them. So the main point is to get how singular are these derivatives when z approaches the boundary of the unit disk. Fine. Now, from now on, we will always assume that alpha and beta are not negative integers and that the sum of the real parts is larger than -1. So that we have these L1 estimates available. And basically, look at this formula number 4, then you get the Poisson kernel, which is constructed from this U alpha beta function. Zeta is the integration variable. It's on the circle, and z is in the unit disk. And this constant is just a normalizing constant, involves gamma function, as you see. And this choice of the constant ensures that this limit is equal to 1. Now, and then you define the alpha beta Poisson kernel of an integrable function on the circle by this formula. It's quite standard, right? And then this alpha beta Poisson integral of f, or alpha beta harmonic extension of f to the unit disk is alpha beta harmonic, because the kernel is alpha beta harmonic with respect to z. And that's the. And now we have HP spaces. We have HP spaces which are defined completely analogously to the classical case of HP spaces on the unit disk of analytic functions or of harmonic functions, whatever you like. Here we work only with P. We don't consider the case P is less than 1. So we take this range of the exponent P. And we have these spaces which are Banach spaces with respect to these norms, completely analogous to the classical case of ordinary harmonic or analytic functions in the unit disk. And now we have this theorem which was known even in the case of the unit ball from this ABC paper. And it provides you integral representation of functions in these kind of Hardy spaces, generalized Hardy spaces. So this is the theorem. It's uniquely represented by a function in LP on the unit cell. If P is equal to 1, you get a measure as expected. And now you might also ask a question about the norms. Is the norm of this representing function psi in LP related to the norm of U, which is given in the unit disk? And it turns out that these Banach spaces are isomorphic, but not necessarily isometrically isomorphic. It should be pointed out, if alpha is equal to beta and both are real, then it's isometric isomorphism, because then the kernel is positive. So then this is a different and better situation in a certain sense. And there is this joint paper where we developed this HP theory in other direction. ABC, they worked in the unit ball. And here we worked in the unit polydisk and considered functions which are which satisfy the system of partial differential equations. So with respect to each variable, the function is in the appropriate space of alpha beta harmonic functions. So that's just a side remark. And now look, let's review the known results, which were known earlier regarding the estimates of the derivatives. Let's start with this formula 7, which gives the formula for the norm of the derivative. Now, derivative is considered as a linear map from R2 to R2, right? And then you have this formula which relates it to derivatives with respect to z and with respect to z bar. This is this formula 7. Now, there is a whole bunch of results which are obtained earlier, and now this is perhaps the oldest one. That's Colonna, 1989, for ordinary harmonic functions. You see, it's bounded and harmonic function, bounded by 1, maps disk to the disk. Then you have this Colonna's estimate. Next group of results is related to so-called T alpha harmonic functions. So we have one parameter, it is real. The case alpha equals beta, essentially. So alpha half, alpha half. So there is this estimate of the derivative at the point z. Then Halfalach and Matejevich obtained the estimate at point 0 for the same class. You see again alpha half plus infinity. So that's sup norm, case p equals plus infinity, supremum norm. This is the sharp constant. And then look at this again. You're assuming that u is continuous up to the boundary, and then you have again estimate in sup norm of the derivative at point z. And then again, continuity up to the boundary is part of the assumption. And then you have this estimate at point z. The most recent is appeared this year, Halfalach Mamdi, and they obtained this estimate. Recall that this is the only result that we review, which the only result earlier, which involves two parameters. Here, alpha and beta, you have two parameters. They are real and are subject to these conditions. And then this is the estimate. This is the estimate of the derivative at point z. All the estimates are obtained in the supremum norm. So no estimates were known such that on the right-hand side you have p norm. You only had p equals plus infinity in all of these results. Now what Jelena and I did, we generalized all of these in several directions. So this is going to appear that it was accepted this week actually. So it's going to appear in Journal of Mathematical Analysis and Applications. So all of our results are formulated for general complex valued alpha and beta, as I said, not equal to negative integers, and the sum of the real parts is greater than -1. Now, we consider full range of parameters p. Earlier results treated only the case p equals plus infinity, so only supremum norm. Then we get sharp estimates at z equals 0 for general alpha and beta and for any p. So any p and general alpha and beta. Then when you ask a question, what if we look at the estimates not at the origin, for general Z, then we improve this latest result by Halfalach and Mamdi. We get a better estimate. In the sense, first we have more general case of complex valued parameters alpha and beta, and the constant is better. Then we do not require, it's not acquire, it's require continuity up to the boundary when the estimate is in the supremum norm. So often authors assume that the boundary function is continuous. Here we have that the boundary function is essentially bounded. And in addition to that, we obtain asymptotically sharp estimates as we approach the boundary of derivatives of arbitrary order. Of course, we are not able to provide a sharp constant in that case, but the rate of growth is optimal as we go to the boundary. So now, how are we going to do this? Well, the first thing is calculate. Just do it by calculation as far as you can, and you get some horrible formula for the norm of the gradient. So phi is in L1 of t, and we get this mess, right? And at point z, this mess of a formula is for general z. However, if z is equal to 0, it simplifies greatly. You get this, which is much nicer, right? And then I'm going to switch to the paper itself. I hope it's be seen here. Okay, let's do it here. So we are able to express at least what happens when z is equal to 0 by this formula, where we have this auxiliary quantity I of phi. It's formula 8, right? And then the desired quantity, the norm of the derivative at 0, is expressed by this sum of two integrals, right? And phi is any function which is in L1 on the boundary. So okay, once again, you start from a function which is integral on the boundary, apply the alpha beta Poisson kernel to phi, get a function which is alpha beta harmonic in the unit disk, take the derivative at 0, and look at the norm. This is the exact formula. This 9 gives you the formula, and this I of phi is the sum of two terms. And then this is a key lemma. It's just by some tricks which are nice, but there's some trick involved here to be able to express this sum in this more compact form. And now let me go to the paper itself. Remember that the norm of the derivative can be expressed as a sum of derivatives with respect to z and derivative with respect to z bar. And now this proposition from the paper itself estimates these derivatives with respect to z and derivative with respect to z bar. That's this formula 17 in just any p norm. Supremum is taken over all phi which are bound in p norm bounded by 1. And you can estimate each of these separately and get the sharp constant for both of them. And now the idea is kind of primitive. Just make a sum of these two, and then you get, as it's written here, you get this estimate. Now this is independent of exponent p. the right-hand side does not depend on P. But this is not the optimal constant. The optimal constant depends on P. And the reason is that the extremal functions in these two supremums are different for the derivative with respect to Z and for the derivative with respect to Z bar. So you get an estimate, fine, even independent on P, but the constant is not sharp. And now the sharp constant, the best possible constant, is given by this first result. For any P, this supremum is equal to the quantity which is on the right-hand side. Q is, of course, the exponent conjugate to P. So this is exact, the best constant. Of course, P equals 1 can be included in a natural way, and that's the theorem. Now, we can specialize. This works for any P. The earlier researchers dealt with the case P equals plus infinity. So now let's see what happens when the boundary function is in L infinity. Then we get, by specializing this theorem, we get this constant. It's expressed by elliptic integral of the second kind, special function. And now we basically get the previous results as a special case. As a special case, when you restrict, when we restrict, there is something with the audio. Something with audio happens strange, but I hope you do hear me.
Yes, everything is perfect.
Yes.
Yeah.
So, okay, then it's fine. Now, what about when we move from the origin to any point Z? Now, again, we have estimate not only in the case of P equals infinity, but for any P. So there is some lemma which I think time does not permit to go into all the details. But here we have a constant which is explicit. This C alpha beta P is an explicit constant which comes from the proof. So I'm not going to look at this. And there is a little bit of improvement even when P equals infinity, it will turn out later on. Look at this exponent. You have 1 plus 1 over P. Here, I'm going to mark it, right? When P equals infinity, you get what you expect in that case, that the derivative has this factor 1 over 1 minus modulus of Z squared. So that's the right rate of growth allowed at the boundary. When P equals 1, you get 2. You get that squared. Again, this is something which you expect from such things, and that's it. Now we get sharper estimates than the previous result. In some cases, even by the not full order of magnitude, but even the exponent gets better than the previous results. So it's a sharper estimate. Now let's turn to higher order derivatives, which were not treated earlier. And the idea is fairly simple. You really only need to differentiate the kernel, essentially this U alpha beta function, and see what happens. And you get basically the same U alpha beta function, right? Multiplied by something which is messy, okay, complicated expression, but essentially it's like a polynomial is in these first 3 terms, right? With total degree K plus L. And And when you do this, which is done by simple induction, then you can differentiate in under the interval. Okay, this is the consequence of what I just said. It has the right order, right? The right rate of growth as z approaches the boundary of the unit disk. And then we again get this theorem, which, okay, now it's of course totally hopeless to get best constants, but we get this rate of growth near the boundary. So with that respect, there are no surprises. It behaves basically what you expect from the harmonic functions or even analytic functions. So this is asymptotically sharp. This is asymptotically sharp. And one might ask, okay, if you impose different conditions on the boundary function. Now, this is LP theory. One might ask, what happens if you say it's not only continuous, we covered that, we have the same estimate for the general continuous boundary function as for the essentially bounded function, the same type of estimate. But if you require more than just simply continuity, you say require it belongs to some Helder class, Helder continuity, or Lipschitz continuity, then what do you can say about the estimates of the derivatives as you approach the boundary? Now, the interesting part would be what's going on near the boundary. And I think that Adel Halfalach has some results in that direction, but not with respect to the derivatives, rather with respect to the function itself, these moduli of continuity, and probably Matejevich as well. And Halfalach's students, this group, I think they work on that area. So that could be one possible future direction of investigation. What happens with the derivatives if the boundary function is better than continuous? So now this is like a kind of digression which introduces us to the next topic. So this was done with joint work with Jelena Gajic, and now the next is something that Professor Matejevich and I worked, and it's already published, this case. Now, just before going into this, to round off this topic of alpha-beta harmonic function in the unity disk, now Gajic, Jelena, she investigated the inhomogeneous case. So now their U is missing. L alpha beta U is equal to G. So you want to solve the inhomogeneous alpha beta harmonic equation, right? With say 0 boundary data, 0 Dirichlet conditions. And then there is Green's operator G alpha beta, which was constructed even in the more general case of the unit ball in the ABC paper. And now you can ask basically the same question. What's going on in the inhomogeneous case? Well, and when you have this Green's kernel and Green's operator, then it enacts on the functions which are defined on the unit disk and belong to some LP space or are continuous. And now this is, as they say, work in progress. And there is, to get some kind of feeling what can be done, this is some of her results. You see that the first one is not related to derivatives; it's related to pointwise estimate of the Green's alpha beta Green's potential. This is the first one. P and Q are of course a pair of conjugate exponents. So this is this one. And now the next one is the estimate on the derivatives, right? And now this is done in the essentially in the supreme node. And now in the meanwhile, there are other results, but now we shall leave the topic and move on to the different setting. And that different setting is the setting of the upper half space and vertical derivatives. Vertical derivatives. So now let me just briefly set up a notation. So the upper half space, right, n+1 dimensional. So the boundary is essentially Rn. And now we have this well-known Poisson kernel for the upper half space, a constant not matter much. And then again, we have in the spirit things similar to what we had in the unit disk. Now we have the harmonic extension. Now these are plainly ordinary harmonic functions, no more alpha, beta, anything, just ordinary harmonic case. And then this Poisson integral of phi is given by here. That's the Poisson integral. And now we are going to deal with moduli of continuity, right? So let me say immediately in advance that there will be some conditions on the moduli of continuity, but these include all the classical ones. I mean, those moduli of continuity which define Helder classes and Lipschitz classes. So this is a general definition, well known for modulo of continuity. That's a function which is continuous, concave, and increasing on the positive real axis, strictly positive except at 0. Omega of 0 is 0. This is also, I missed that, but that's. And now we need some condition on the moduli of continuity. And this, we called it, Professor Matevich and I, we called it condition A, for example. And that's the condition. And it's important to note that these omega of t equals t to the power alpha satisfies condition A for any alpha between 0 and 1, including 1. So this classical Helder and Lipschitz, that is included here. Now what do we have here? Now we are going to investigate the vertical derivatives. Okay, that's what are we going to do. It's always easier to control the tangential derivatives. So look at the notation. X, y. X is Rn, y is greater than 0. Partial derivatives with respect to x1, x2 up to xn. This is easier to control, to get estimates on this. The difficult part usually is to control the vertical derivative with respect to y variable. Regarding these Poisson extensions. So now let's go here. Now you have a function phi which is given on the boundary of the upper half space in LP, and assume that at fixed point x is 0, it satisfies this omega continuity. Let's call it omega continuity, right? Then the harmonic extension satisfies this estimate. You see, here you have estimates of the derivatives with respect to the tangential directions, x with respect to x1, x2, and so on. So then it's the derivative has this behavior. Think of, say, that the boundary function is Lipschitz continuous, right? Then omega y is equal to y, right? And then you have the boundedness of the derivatives with respect to x1, x2 up to xn, which is to be expected, has to be expected. So this is a lemma. It's probably even known, who knows? I mean, you cannot search all the literature, but that's a fairly simple thing to do. Proof. we will going to skip the proof. Basically, you differentiate under the integral sign, and then see what happens. Use the continuity, omega continuity at a given point, and so on. And here you have a condition. Now I cannot, here I can mark it. So you have this a condition, it appears in the estimate of this last integral. So I'm not going to bother you with the proof. And one of the reasons is that I have to, it wouldn't be very useful anyway. And then even you can get an explicit constant. Now, how do we connect estimates with respect to the tangential variables with the vertical variable? Now, another point, another notion comes into the play. This is the system of conjugate harmonic functions. So you assume you have n+1 harmonic functions, u0, u1, u2, and so on up to un on the upper half space. Now, it's a conjugate system of harmonic functions if this formula 18 holds. Now, it's important to note if we have n equals to 2, that this is just the classical Cauchy-Riemann equations, which you know from the complex analysis. So if you have this system in dimension 2, then u0 plus I u1 is an analytic function in the upper half plane. Now, how do we get these systems? Well, you take ordinary harmonic function in the upper half space and take derivatives with respect to y variable and then x1, x2, xn. You get n+1 harmonic functions, and they form a system of conjugate harmonic functions. So differentiating a harmonic function of n+1 variables gives you a system of conjugate harmonic functions. And it's also related to the Riesz transform, singular integral operators, which will become important in a moment later on. Yeah, this is what I said. It's written here. And now, this relation between conjugate system. So if you assume let's see here notation. Fj, j goes from 0 to n. So you have n+1 harmonic functions which form a conjugate system. And if you have an estimate of the derivatives of fj with respect to xj of this type here, right? Oops, something is, yeah, now it's okay. Then you can estimate the derivative with respect to the vertical variable of the first one, because they're interrelated, by this equation 18. So, because this sum is a 0, right? Then you can express the first one, df0 with respect to dx0, which means with respect to dy, as the minus sum of the remaining ones. And then you get this. Now, we have these Riesz operators, which I'm not going to explain what are they. They are singular integral operators. They appear in harmonic analysis all the time. They're bounded on LP, except for p equals 1 and p equals infinity, where they're not bounded. And now, this is the main, basically the main thing. Let me explain slowly without rushing. You have a function which is in LP on the boundary. the upper half space. So this is LP of Rn. P is within this range. And then apply the Riesz transforms. There are n Riesz transforms of this function f. And you get functions f1, f2 up to fn. Right. You extend this boundary function f to the upper half space. So make the Poisson, by this Poisson integral formula, you extend f to the upper half space. Now, omega is a modulus of continuity with this A property, and you have a subset E of the boundary. And now assume that these Riesz transforms of f, these functions fj, they are, let me say, omega continuous at each point in that set E. Then you can estimate the vertical derivatives of that extension above each point of the boundary that belongs to the set E. Now, it's not that complicated as it looks. At first, basically, it's a result on a fixed point. For each point, you fix a point x in E, and then prove the result for that point E. But what is important to note is that what governs behavior of the vertical derivative are these Riesz transforms of the function f, and their behavior near the boundary point. So this condition is the behavior of the Riesz transforms at points belonging to the set E. And it's proved basically using these conjugate systems of harmonic equations, because when you extend each of these fj's to the upper half space, well, fine, then you get together with u, get a system of conjugate harmonic functions, and you get this estimate. Now, this is basically the end of the talk, and I thank you for the attention. And these are two settings which were of interest to people here in Belgrade and in Banja Luka, and also elsewhere. It can be, we can go into many different directions. Professor Mateljević with his PhD student, I think, Nikola Mutavčić, they investigated also hyperbolic harmonic functions and similar. So it's a huge area. I just selected those two. Now, thank you.
Well, thank you, Professor Milos Arsenovic, for a very nice presentation. We have time for questions, please. Yeah.
Thank you for your talk. I just have a comment that this last part about the harmonic conjugate functions may be interesting for people doing Clifford analysis, because this system is one of the main objects of Clifford analysis. In fact, just a small comment that around this formula 18, obviously it's Cauchy-Riemann when n is equal to 1, not 2.
Yeah, yes, when n is equal to 1, right. Yes.
Thank you for the interesting talk.
Yeah. Regarding Clifford algebras, there was a talk in Yerevan, which was something in that spirit of doing this kind of analysis. But now I cannot recall details. But I don't know if Alexey remembers. There was a talk about related to the analysis
You probably meant Helmut Malonek?
Could be.
For sure.
Yeah. Yeah. Yes. Hello. Yes, that was your talk. Yes. Yes, but we talked about yes.
Okay,
but now I cannot.
If Helmut is here, he can repeat his talk now.
Yes.
We
Right.
have 10 minutes, actually.
Yeah. Now I want to. Well, I'm not asked questions, but now I'm. This is to comment on this. Let me see. There is what Yelena is doing. I think there were results on this type. I mean, people investigated these greens alpha beta potentials, right? But and obtained partial results. Now here the attempt is to push it to more general case, and the may I say another comment? It's often you cannot easily apply this general theory of elliptic second order elliptic operators because this is degenerate, and if you want to get sharp estimates, then this general theory in the spirit of Gilbart, Trudinger doesn't work because they have quantitative results.
Okay. So maybe more questions? Milos?
Yes.
Okay. I have one question also. In your estimates, when you have a function or graduate of function on left side, on right side, you have behavior of this function. Oh, the value that estimates the behavior of the function.
Right.
But sometimes you do have there a normal function, sometimes not. Like LP norm, for instance. I wonder, in the estimates that you don't have a norm of a function, it is just impossible to get it, or you just don't care about it?
Well, I'm not sure if I understood precisely the question, but let's look at some of the.
Well, like in 13, you have normal function in an infinity. Okay?
Norm. Yes.
Normal function.
Norm,
yes. Sometimes
normal function.
Norm. Sometimes you don't have a norm there.
But that's because if I don't have a norm, then on the left hand side it's assumed that the norm is less than or equal to 1. Yeah, so if you scale, you can get for the general. You see, when you have an estimate, it's kind of trivial remark. When you have an estimate over all functions, say phi of norm LP norm less than or equal to 1. Then on the right hand side you have a constant, right? But then this implies general results, right? For without any restriction on LP norm of phi. You just multiply by the norm P norm of phi on the right hand side. Yeah, I understand now what's the question, but it's just a matter of convenience. Look, as for example here, right?
Yeah.
In that case, you have this on the right hand side, right?
Yes.
But
0 at a 0.
Yeah, okay, but it's you have this estimate. And
Like-
here you don't have norm here, right?
Yes.
But that's
Yes.
because here it's assumed that because this is assumed.
Yeah, but my question was better to estimate in Lebesgue spaces, because it's, well, I usually use these estimates when I need to prove some boundedness in the Lebesgue spaces. It's very useful to know that your function is estimated by some behavior depending on the variable z and up to norm of a function.
Yeah.
Even now, for instance, we are doing paper on grand Lebesgue and other spaces, and we use this kind of estimates to prove some embeddings. So it's useful to know that you can estimate pointwise a function having on the right side a certain norm. But I understand your arguments, of course. I understand your arguments.
Okay.
But it's always useful and it's good to have this kind of written explicitly, you know.
Yes.
And also besides the Lebesgue space, I just sent you an article that we wrote in 2017. It was kind of unique experience of doing harmonic functions and estimates of harmonic functions, but we did estimates for classical harmonic spaces in Lebesgue and variable exponent, I guess, Lebesgue spaces, Morris spaces, and Orlich spaces. So my question is, what about the other kind of spaces, like Orlich spaces, maybe Morris spaces? Do you have some plans on this?
No, but thank you for the suggestion, because we haven't planned this direction. That would be quite something, because we, frankly speaking, we attacked at first these classical things, right? And because people did certain things for one parameter case. So the first focus was, okay, let's see general alpha and beta and general LP norm, right? And now the next to go to say Orlich Lebesgue spaces or other conditions on the boundary functions which involve some kind of finer points of continuity, like as I mentioned, Helder zone, and even to variable exponent spaces when P depends on the point. That's another. This is level up, right?
When you estimate,
it's level up. And there are two things. I mean, one is the estimates at a given point of the function itself. This is easy, I think. I mean, that should be probably easy. We haven't, but the estimates of derivatives, that's some work has to be done, and then these continuity properties, as I mentioned, there were already attempts at Helder. So if you have a Helder continuous function on the boundary, and then you extend it alpha beta, then do you get also Helder continuous function on the whole closed unit disk? Well, sometimes yes. In fact, always yes, but sometimes you get loss of the exponent. That's one of the interesting things that happens. But yes, for these spaces, yes, I agree that Orlich Lebesgue, that would be now generalization of what can we say then about the size of the extension and then of the derivatives. Maybe something, I don't know. I mean, but that's a good question. We haven't thought about it. And
because from my experience, I know that extension from LP to Mori not so bad. I mean, you can do this because in any case, when you define in Mori space, you define by using the Lebesgue norm. Of course, there are some
difficulties
and the supreme moments and stuff like this. But in any case, you inside of supreme you have Lebesgue norm. So
yes, now I understand. Okay, yeah.
And
Okay,
Orlich is different, but also if you have some restrictions on
defining function.
Kind of doubling property, stuff like this, you get very nice estimates involving the inverse Orlich function. Or inverse Young function, sorry.
Yeah. Well, the first step would be to look at what people know about the classical harmonic case.
Yeah, but you can see at in our article I sent you just by email.
Yeah, okay, good.
Yeah.
Thank you.
So there we have the case of holomorphic functions bounded in Berman projection, and then the case of harmonic function also bounded in Berman projection.
Yes. I remember. You know, you had this talk about which covers so many. So I mean, general scheme of things to get the boundedness of everything. Yeah. Okay.
Okay, good. Well, maybe more questions. Well, we had very nice discussion, and well, if no more questions, then let's thank speaker again for very nice presentation.
Thank you. Thank you,
Thank
folks.
you.
Thank you, folks.
Thank you.
Thank you, Milos, for presenting such a great talk, and see you.